Good morning and good afternoon and good evening, everyone. This is Nobito Yamamoto from University of Electro-Communications, Tokyo. Okay. This is my title on verification methods for conservative systems. The authors are me and Koki Mita. This is today's story. In verified computation of ODEs, Lohner method is widely used. This is a method based on theta expansion and can achieve high accuracy, taking high orders of theta expansion. It is known that drift of the trajectories happen in numerical calculation of the solutions of conservative systems. In order to avoid the drift, high order theta expansion should be used in Lohner method. We try to avoid the drift by calculating the conserved quantity instead of using high-order theta expansion. Our final goal is as follows: to develop verified numerics as tools of analysis, which is so convenient to the users, especially the people engaged in simulation of phenomena. However, rigorous computation is not always necessary in simulation. Then we aim, one, to develop tools in order to understand the mathematical background of the phenomenon. Two, to develop tools to use in development of computation scheme of phenomenon simulations. Concerning two, our special target is conservative finite difference schemes, which have been developed by several authors, especially Professor Matsuo in Tokyo University, and Professor Furihata in Osaka University. Today, we treat a toy problem to see what happens in combination of the Lohner method and calculation of conserved quantity. Our goal is our problem is a conserved system of complex valued ODE. This is also written by using real-valued functions x and y. The conserved quantity is h, and the curve hz equal constant gives the solution trajectories. This is a figure of exact trajectories. The purple curve means hz equals 0. Moreover, we know exact solutions in this case, but approximate computation is so hard. This is an approximation. The trajectory of approximation starting with z equals 7 until t equals 30 using ODE 45 in MATLAB. While the scheme is fourth order accurate, we cannot obtain a closed orbit. Calculate until t equals 40, too bad. Starting from z equals 40 until t equals 20, these are terrible results. It is better to use computation methods to keep conserved quantities. For example, conservative finite difference scheme. We asked Professor Furihata in Osaka University to compute this problem by his method. This is the result, very good. In case of verified computation, a Lohner method with high order theta expansion also gives good results. But if we restrict ourselves to fourth order theta expansion, the results contains rapidly increasing of the interval, like this. What we consider first is as the following method. 1. Divide the box obtained by Lohner method into a number of small domains. 2. Calculate the conserved quantity h for each small domains using interval arithmetic. 3. Select the domains where their h include h0. 4. Compute solutions for several steps by Lohner method starting with the selected domains. 5. Take an interval as a convex hull of the resulting boxes obtained by 4, and then continue. We expect the results of 5 would be better than the straightforward continuation of Lohner method. However, it is no good. Indeed, the results are better, but just a little. The resulting boxes of the step 4 give good runs, but their convex hulls become large. Especially, errors along the trajectory cannot be reduced. Then we propose second method as follows. 1. Divide the boundary of the box obtained by Lohner method into a number of small segments. We calculate the conserved quantity h for each small segment and select the segments where their h equals h0. 3. Calculate the inner product of n and fz for the outward normal vector n and the flow fz on each selected segment. These values allow us to classify the segments into two groups, a set of incoming segments S in and a set of outgoing segments S out. 4. Take two intervals I in and I out as convex hulls of the boxes computed by Lohner method from S in and S out, respectively. 5. And then continue. But know that succeeding process for I in only computes incoming segments and that for I out only compute outgoing segments. Here is an illustration of incoming segments and outgoing segments. The red box is the result of Lohner method. The curve implies Hz equals H0, and the arrows denote the flow Fz. And this is S in, this is S out. Okay, we choose them. Usually the intervals in and I out are so small, and then S in and S out in the next step are also very small. Now consider P in as incoming point and P out as outgoing point, where this set denotes the trajectory. Okay. Then the exact solution is specified as a point on the trajectory between P in and P out. Note that in this case, we know the exact trajectory by Hz equals H0. Then what we want to know is the point on the trajectory which denotes the solution. Therefore, an error on method 2 implies an arc on the trajectory. These are incoming points near around the box obtained by Lohner method from Z0 equals 7 and T equals 1.5. Okay, these are boxes obtained by Lohner method, and these are incoming points starting at this point. Okay, this is an enlarged view of incoming points and boxes. The maximum length of the incoming segments is so small. These are outgoing points, very far from the boxes. The maximum length of the outgoing segments is also so small. In order to see how incoming points and outgoing points move apart, we plot them for the same time step. This is an incoming point and outgoing point corresponding to the same time t equals 1.5. Okay, they are very close. This is for t equals 1.95. So close. This is t equals 2.2. Still close. This is t equals 2.45, a little bit apart. And this is t equal 2.7, so apart. And this is 2.95. They are two apart, and the exact point is here, okay, between incoming point and outgoing point. And this figure shows incoming points and outgoing points corresponding to the same time, t equal 2.95 and t equal 3.0. Okay. This point for t equal 2.95. Okay, and this is incoming, and this is outgoing point for t equals 3.3 as 3.0. Okay, then why they are going to move apart? This is exact solution. This is a curve of exact solution. Okay, calculating of exact solutions show the speed of moving is changing. Okay, this part and this part have so fast moving, and this part and this part are so slow. Okay, this makes the difference of incoming points and outgoing points. Okay, now we show you our conclusion. Combination of Lohner method and calculation of conserved quantity gives a new aspect of error distribution. In this case, the trajectory can be obtained explicitly. Thus, the error bound means an arc on the trajectory. In physics, Hamilton systems have 4 or 6 dimensions. We will investigate such cases. It should be seen how it goes in the cases with multiple conserved quantities. For example, Hamiltonian and symplectic relation. Finally, we approach to develop numerical verification methods as supporting tools for development of computational schemes. Okay. And this is the references. Now, have a good day and have good meals, especially good fish. Okay, thank you. Bye-bye.